Well, now on 2, we take a look at a surveying problem in maths topics.
This series has been specially designed for recorded use. Full details are in the notes for teachers. Let's start here. By this construction, we form a new triangle. Each side of the new triangle is 3 times the length of the original one. What about its area? This time, a reduction. Whatever the value of the scale factor, this method of construction is called enlargement. The shape always remains the same. Only the size changes. Using a different center of enlargement and the same scale factor. Different centers of enlargement with the same scale factor give triangles all the same shape and size, but in different positions. Anyone who's ever used a map out in the country will have seen the words Ordnance Survey. This is the official survey and mapping organization in Great Britain. These surveyors need to check the exact height of the corner of the field by this gate.
Well, this looks a good point. Yes, there's...
Here it is on an aerial photograph.
There.
This is one of a pair of overlapping aerial photographs which also show a point whose height they do already know, very accurately. Later on, these will be used in a machine which can convert photographs into maps. This is the left-hand photograph. The right-hand photograph is already on the machine. What the operator does is to adjust the positions of the two photographs until he appears to see a three-dimensional picture. On the working drawing, he has already plotted, in the correct positions, several points whose positions and heights above mean sea level are known. He exchanges the microscope for a pencil and checks that the plotter is over the correct point. Now he makes the photographs move, so that the small black dot in the middle of the screen follows an edge of something, in this case, a road. His foot controls the up and down movement of the pencil, which traces out a broken line exactly corresponding to the movement of the black dot along the road in the photograph. And now, a continuous line. But this map making can't even start until the surveyors have found the height of the corner of the field. They do know the height of this point. Here it is on the existing map. It's called a triangulation pillar.
And that's the pillar up on the hill there. Fine.
It's about 1 kilometer between the 2 points. The top of the pillar is already known to be 129.21 meters above mean sea level. But what matters is that they know the height of the hill above sea level, and they want to find the height of the corner of the fence. So it's only the difference in height that they need to measure. That's this distance. They can't measure it directly because this point is deep inside the hill. The only distance they can measure is this one. So, how do they measure, through the air, a distance of about 1 kilometer?
OS70 to OS69, over.
OS69 to OS70, receiving you, over.
Measuring now, over.
What they do is to transmit a beam of infrared light down to the fence junction, where a pair of prisms reflects it back to the transmitter. The instrument notes the travel time of the light. Knowing the speed of light, it computes the distance to the prisms, 930.387 meters. Now they know this distance, but they don't yet know its direction. They need to measure an angle. You can't do that with just a light beam, so they use this instrument, a theodolite. First they get it level, using built-in spirit levels. They're going to find the angle through which you would have to tilt the theodolite from the upward vertical until you were looking at the reflecting prisms. If you've ever used a theodolite, you'll know that the view through the eyepiece is upside down. You can see the surveyor's orange anorak and the tripod with the prisms. The theodolite is turned till the horizontal hairline lies halfway between the two prisms. Through the other eyepiece, he reads off the vertical angle. The upper scale tells him that it's between 91 and 92 degrees. 1/60th of a degree is called a minute of angle, and 1/60th of a minute is called 1 second of angle. The lower scale indicates 15 minutes and 25 seconds, an extremely accurate measurement. On our diagram, we've exaggerated the angle, which in reality is just over 1 right angle. In ordinary decimals, that's 91.2569 degrees. We'll use this accurate figure later, but for the moment, we'll round it to the nearest degree, 91 degrees. The distance through the air down to the prisms was 930.387 meters, but we'll call it 930 meters while we see how to calculate the height difference we need. To find the length of the vertical side of the triangle, we make a copy of the triangle and calculate the angle next to the 91 degree angle by subtracting from 180. we use a scale factor, in this case 1 over 930, to create a triangle with hypotenuse 1 meter. The length of its horizontal side will be cos 89 meters. Reverse the mapping to get the corresponding length of the original triangle. Now use the more accurate figures. Of course, we can't rely on the last digits. Even this distance is to the nearest millimeter. It's the difference in height between the triangulation pillar and the prisms at the corner of the field. We already know the height of the triangulation pillar. Subtract, and for a small scale map, round it off to the nearest meter. We need an angle inside the triangle. The 930-meter side is the hypotenuse. The length we want is the adjacent side. The required length is 930 cos 89 meters. Now use the more accurate figures. Of course, we can't rely on the last digits. Even this distance is to the nearest millimeter. It's the difference in height between the triangulation pillar and the prisms at the corner of the field. We already know the height of the triangulation pillar. Subtract, and for a small scale map, round it off to the nearest meter.